Okay, thank you for being here. Yesterday, we have posed some very basic cases of the so-called realization problems in terms of projection volumes of convex bodies in L4 and higher dimensional spaces, and also for homology classes and realizing them by a subvariety. Today, I'm going to tell you a general framework in which we can pose such realization problems. And that is the framework given by Lorentzian polynomials and matroids over triangular hyperfields. So I'm going to very quickly tell you what Lorentzian polynomials are. This is developed jointly with the Peter Brandon. And most of the new stuffs about the relationship to matroids over triangular hyperfield will be based on joint work with Matt Baker, Mario Kummer, and Oliver Lorentzian. So here is the definition, one of many possible definitions of a Lorentzian polynomial. So we're going to work with homogeneous polynomials, always in n variables and with non-negative coefficients. When I'll have to refer to the degree of f, it will always going to be d. And the definition is that we say f is a Lorentzian polynomial if for all exponent vectors alpha, non-negative, the partial derivative of f with respect to alpha, which means that you're taking the directional derivatives in coordinate directions that's been given to you by alpha, is either identically zero or log concave on the positive ordinate. For example, if alpha is 1, 2, 1, you take the partial derivative with respect to first coordinate one time and second coordinate two times and third coordinate one times. And you require that the result to be log concave. But we're going to focus only for the simplicity of exposition, the case of scare-free polynomial, where the language reduces to simpler or at least more familiar language of matroids. By scare-free polynomial, I simply mean a linear combination of scare-free monomials. So we're going to sum over all the d element subsets of n, which will correspond to monomials. And each such monomial, x to the s, will have a coefficient p to the s, which I assume to be non-negative. In this case, things are simpler because you don't have to really remember about all the partial derivatives. In this case, you can see that f is Lorentzian if and only if log of f is a concave function on the positive ordinate. In other words, you don't have to think about the conditions imposed on the partial derivatives. Why? Because f is a scare-free polynomial, it means that it is affine linear in each one of the variables. So the leading term of this affine linear function will be the partial derivative with respect to that. In fact, is a limit of f. So if f is a log concave polynomial, then all the partial derivatives, being a limit of it, will be automatically log concave. So we're just talking about scare-free log concave polynomials. And that is what f means to be Lorentzian. And the slogan here is that the space of scare-free log concave polynomials is a Grassmannian. That is the one sentence that you can take away. And this sentence, as you will see, is actually a true statement if you interpret some of the words used in the sentence in an appropriate way, including the word Grassmannian and the space and the word is. Okay. There are two main examples. Maybe these are the only two examples that you may care about of Lorentzian polynomials, and they correspond to realization problems in convex geometry and algebraic geometry, as you will see in the next lecture. So the first example is a Lorentzian polynomial constructed from a sequence of convex bodies, C1 dot 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 Cn in R to the D. And then what you do is you take the general linear combination, here Minkowski linear combination of Ci's with non-negative coefficients, so that you can get a new convex body, and take the volume of it and see what kind of function you get as you vary the coefficient xi. And Minkowski, long time ago, has observed that this function in x is in fact a homogeneous polynomial of degree d in n variables, x1 to xn. And the main result of the so-called Brun-Minkowski theory is the statement that this polynomial is Lorentzian. In particular, it is a log concave function. And this statement encompasses all the isoperimetric type inequalities that exist between the so-called mixed volumes of convex bodies, which are solutions of such polynomials. The second example comes from algebraic geometry. So let's say you have a d-dimensional projective variety X over some field, and you have Neff divisors d1 to dn. And you play a very similar game. This time, you take a general linear combination, say with non-negative coefficients of di's, and take the self-intersection of it and integrate it to turn it into a number. In this way, you get a function of x, and this function, as you know, is a homogeneous polynomial of degree d in n variables xi. And you may be familiar with the statement that such polynomials, also called the volume polynomial in algebraic geometry, is log concave on the positive portent. And then the statement that this is actually Lorentzian, the partial derivative statement, is in fact almost exactly the same statement obtained to the hyperplane section corresponding to the partial derivative that you want to look at.
Way of thinking about log concave. You have a way of thinking about log concave?
It is what it is. And maybe I can interpret the question as how do you prove it or justify it? And there are several different ways, but every single way eventually boils down to Hodge theory, which says that the Hodge-Riemann relation exists in H11. It's amusing to note that this so-called Brun-Minkowski theory developed by Minkowski and Alexandrov and others boils down to almost exactly the same type of statement on one positive eigenvalue condition. So, but today, I'm going to just forget about convex bodies and projective varieties, but just consider the geometry of the space of log concave polynomials. And here I want to convince you that the collection of all such is actually a Grassmannian. If you consider the coefficient in front of each one of the sphere-free monomials as the Plücker coordinate of the corresponding point f. So let's start from the most simple case of quadratic forms. So I'm just talking about set of quadratic forms, which is log concave. And I'm going to look at the part where every coefficient is strictly positive so that I can draw the pictures in logarithmic charts. I'll take the coefficient-wise logarithm to draw pictures. Cauchy interlacing theorem in linear algebra can be used to show that this log concavity condition is in fact a spectral condition. L to n, not to denote that we are looking at the open set where every coefficient is positive, is simply the set of all n by n Lorentzian matrices Pij where PII is 0 and PIJ is positive. So this is the, if you recall from yesterday's lecture, a matrix is Lorentzian if it has non-negative entries and one positive eigenvalue. So the non-negative entries corresponds to Hodge-Riemann relation in H00, 0, and one positive eigenvalue condition corresponds to Hodge-Riemann relation in H11. But it is what it is, and it's a linear algebra notion. And clearly, this set admits what I would call a torus action, which is simply the scaling of the n variables. So Pij goes to lambda I, lambda j, Pij. And if you think everything in log coordinates, this scaling action translates the translation action coordinate-wise of and choose two coordinates, which are the Pij's. So let's start from the case we have seen yesterday. This is the case when n equals 4. And we are looking at the set of all 4 by 4 matrices with 0 on the diagonal with one positive eigenvalue. In this case, I have 6 off-diagonal entries, and I can use the 4 scaling actions to kill 4 of the variables, normalize it, and then I'll have 2 variables that are left, x and y. These x and y, if you work out explicitly, you will notice that it is the so-called cross ratios of Pij's. And you can compute the determinant and check that such a matrix is Lorentzian if and only if determinant is non-positive, and that determinant is x minus y squared minus 2 times x plus y plus 1. And you can chart the region of interest as the inside of the parabola, where you're missing 2 points at infinity, where some of the off-diagonal entries become 0. And if you draw the same picture in log coordinate, it becomes a picture that you might be familiar with. So it looks like an amoeba with a tentacle inside, spine inside, and that spine is that of the tropical line. But as a space, topological space, it is an open subset of the disk that's obtained by removing 3 points at infinity. And it's in particular a manifold with boundary. The boundary in question being S1 minus 3 points. So let's think about this S1 minus 3 points more carefully. What is this space? And I claim that this space is a very familiar Grassmannian, which is the Grassmannian 2,4 over the real numbers. So not a funky Grassmannian, the usual Grassmannian. And then I'm going to scale out the 4 torus actions. And as we know, such quotient can be identified with the moduli space M04. So the moduli of 4 points on P1, where I'm just looking at the interior points. And as you see, such space is also S1 minus 3 points. And the claim is that the two S1 minus 3 points are truly identical spaces. How? The way the isomorphism is given by the map that sends the Plücker coordinates of the usual Grassmannian Pij into the quadratic form with the coefficient Pij squared. And this sentence contains many, many little claims at the linear algebra level. First, I'm claiming that if you look at the matrix Pij square, it will have one positive eigenvalue if Pij satisfies Plücker relations over the real numbers. And not just that, it will also have 0 eigenvalue because I'm claiming that the image lands on the boundary of the Lorentzian matrices. And it's not hard assertions, but you have to think a little bit. And the catch here is that this isomorphism is in fact a base change from R. And the thing that you will see shortly is the answer to the following question. The base change from R to what? And in fact, you have seen, you could have guessed what the answer should be. because I'm taking the square of the absolute value of Pij, and you have seen what the T2 plays a role in realization problems yesterday during the whole school. Here is a more interesting example, maybe at the boundary of what you can reach by linear algebra computations. But this is the end result of the analysis. If you try to understand the same space of 5 by 5 Lorentzian polynomials with zero diagonal, modulo scaling, then you'll again get a manifold with boundary. The boundary in this time S4 minus the Peterson graph. And the Peterson graph is not an arbitrary Peterson graph. It's the canonical Peterson graph that lives inside R to the 5 choose 2 modulo R, which is the natural ambient space for Grassmannians. So in R to the 5 choose 2, there are standard vectors Eij, and if you connect those Eij's in the Peterson way, you get a two-dimensional fan. And if you intersect that fan with the unit sphere, maybe after taking log of the coordinates, you get the locus where you should remove. And this is a very, very concrete linear algebra assertion. I'm saying that if you look at 5 by 5 matrices with zero diagonal and one positive eigenvalue, and if you try to make some entries small and small so that they approach zero, while keeping the condition that your matrix has one positive eigenvalue, I'm telling you that you cannot do this in arbitrary way. You can only do this when the variables that you are shrinking or increasing simultaneously approaches to the points on the Peterson graph at infinity. Okay, so what is this Peterson graph? Or what is this S4 minus Peterson graph? It turns out that it is, again, essentially a Grassmannian that we know and love, the Grassmannian 2,5 over C. So modulo torus section, this is the complex points of M05. And the claim is that there is a very natural map from M05 to the space of 5 by 5 Lorentzian matrices. The same map that sends Plücker coordinates Pij to the absolute value square. And it turns out that this is a double covering because it will send two complex conjugate pair of points to the same real matrix, and it will be ramified along the real Grassmannian to 5. And again, this map you will see is a base change from C to T2, and there is a natural morphism from C to T2, as you see. And as you can guess, if you know the M05 bar, you'll know that its natural compactification has boundary that looks exactly like the Peterson graph. And not surprisingly, this map from M05 to the S4 minus Peterson graph extend to M05 bar to S4. So a map between four-dimensional real manifolds. So let's recall some basic facts about Grassmannian. What should be the Grassmannian? The Grassmannian D, n of k is the set of all these spaces of n, and it lives inside P to the n choose B. You send the row span of a matrix A to its so-called Plücker coordinates with this maximal minors, D by D minors, where B ranges from all D element subsets of n. And the image is defined by the so-called Plücker relations. There's one relation for a pair of S1 and S2, B minus 1 set and B plus 1 set, and it should satisfy such a relation, where you sum over every element x in S2 but not in S1. It's a quadratic relation where you have to put the appropriate sign for every term. For example, Grassmannian 2,4 is defined by the beloved equation that we have played with yesterday. And we're going to consider such a zero set not over a field, but more generally, the so-called tract. So a tract is a multiplicative monoid, so you can multiply two things with an absorbing element 0, such that the set of non-zero elements form an abelian group, the unit group. So far, everything is exactly the same as a field. The only new thing here is that we give up the idea that the addition should be a binary operation. Addition is supposed to be you add two things and you get a new element. But this is oftentimes unnecessary to do the geometry, where you only care about the zero set. So you only want to know when a sum of many things equal to 0 or not equal to 0. And the tract is exactly the structure you get by remembering the multiplicative structure together with things that sum to 0. The things that sum to 0 is so-called the null set. It's an ideal of the formal linear combination, non-negative linear combinations of non-zero elements of F. And it should be an ideal in N to the F plus, as we can see in the first item. And then the requirement is that there is an element that we call -1 inside F, such that for every A and B, A plus B is in the null set if and only if B is -1 times A. And the last line is an optional definition that makes the geometry nicer in some situations, which is called the fusion axiom for fusion tracks. It says that if alpha plus z is null and beta minus z is null for some alpha and beta and z, then you can combine these two relations to get a new relation saying that alpha plus beta is null. So every single example that we're going to see in today's lecture will satisfy this additional axiom. So an example. So every field is a tract in the obvious way. So you simply set the null set to be the formal sum of elements that literally sum equal to 0 in your field structure. And this construction extends in exactly the same way to partial fields, where you can only sometimes add two things, and to hyperfields, where you can add two things and get multiple elements. And actually, this defines a fully faithful embedding from the partial hyperfields to tracks. And if you know which elements sum to 0 in a field, you know the field. More exotic examples, but actually very nice and natural ones, is the so-called regular partial field F1 plus minus. This is the 0 and 1 and -1 with the obvious multiplicative structure where the null set is as small as possible. So 0 is null, 1 minus 1 is null, 1 plus 1, -1 minus 1 is null, and so on. This is the initial object in the category of tracks. And on the other end, you have the Krasner hyperfield where things are as null as possible. So this is the Krasner hyperfield K on 0 and 1, where 1 plus 1 is null, 1 plus 1 plus 1 is null, and so on. And this is the final tract. Every tract maps uniquely to it. And our object from yesterday, the triangular hyperfield, you can think of it as a tract on the non-negative real numbers where sum of elements is null exactly when A1 to AN are the side lengths of an n-gon in the plane. So this is some linear inequalities between AIs. And it is satisfied the fusion axiom in the sense that you can break any null relation into three-term relations, like fields. Most of the tracks, every null relation comes from three-term null relations, saying that A plus B plus C equals 0. And this is why the triangular hyperfield is called that way. So every relation comes from a triangle. If you take the limit of TP, I have asserted yesterday that the limit goes to 0 is the tropical hyperfield, where the sum of AI is null if and only if the maximum among the AI appears at least twice. For example, here, if you look at the condition x plus y plus 1 equals null, equals 0, you see the familiar picture of the tropical line like that. On the other end, T infinity is the degenerate hyperfield, which has the null set, where sum of AI is null if there are at least 3 non-zero terms, or if the first 2 terms are equal. So there are many interesting tracks, but more importantly, there are many interesting examples of morphisms of tracks. For example, f1 plus minus being the initial object maps uniquely to C, sending 0 to 0, 1 to 1, and -1 to -1. And the absolute value map is a tracked homomorphism from C to T1. This is the answer to the question. If you know that 3 complex numbers sum to 0, what can you say about the absolute values of the 3 complex numbers? The answer is triangular inequalities. And the T1 uniquely maps to the final tract, Grassmannian Gr K. And interesting fact here is that the final tract has a unique section to T1, sending 1 to 1, because there is an n-gon with all side lengths equal to 1. And T1 is isomorphic to TP using a map A to AP, and the identity map is a morphism of tracks for P less than or equal to Q. And now we can make the statement that I asserted yesterday that T0 is the limit of TP as P goes to 0 in a precise categorical sense. So the category of tracks has very nice properties, including the existence of products. And you can do a really fun computation, like says that the product of F2 and F3 is the initial tract F1 plus minus. Okay. So having a track, we can talk about the Grassmannians more generally, which you simply set Grassmannian T and F to be the set of solutions to Plücker relations. Because you know which n tuples sum to 0. And the morphism of tracks gives the morphism or map of sets of GRDN F1 to GRDN F2 by definition. And all this is very closely related to the very classical combinatorial structure introduced by Hassler-Whitney in the 30s before he turned to singularity theory and vector bundles and that kind of stuff. So this is a definition of a matroid, one definition. And you say that the rank D matroid on N is a collection of D element subsets of N that satisfies the symmetric exchange property. For any B1 and B2 in the collection and any element I1 in B1, not in B2, there is I2 inside B2 minus B1 such that B1 minus I1 plus I2 is in the collection, and same for B2 minus I2 plus I1. So I used to be allergic to any statement that includes more than 3 quantifiers. So, and I think the same is true for many of us, maybe not all, but I'll show you shortly another characterization equivalent to this, which uses far fewer quantifiers. But this is the definition. The other definition was, in a sense, accidentally found by Gelfand, Goreski, McPherson, and Serganova when they were studying torus orbit closures inside the Grassmannians. And it goes as follows. Instead of looking at collection of subsets of n, you look at each one of the subset as a 0, 1 vector inside Rn. And you take the convex hull. And the condition defined by Whitney is equivalent to the condition that all the edges of the convex hull of these 0, 1 vectors has a direction which is a root system of type A, EI minus EJ. Now you can imagine matroids of type D, what they should be, and so on. For example, if you have a graph, any graph, and if you collect all the span trees of it, and then it will become a matroid. That's a Fermat's theorem, very classical. If you view it as a polytop, you spanning tree as a 0, 1 vector, you get a simplex. And if you have a set of vectors in a vector space, for example, these 4 vectors in K2 for K field, and collect all the bases of K2 contained in this collection K, then you get the matroid, the so-called realizable matroid. So for these 4 vectors, you get either the octahedron as the polytop, or one vertex deletion of it, depending on the characteristic of K. Because the notion of linear independence depends on what your K is. Oh, edge directions. You take the convex rule of the vectors e to the b, you get some polytop. It will have finitely many edges, and the requirement is that every single one of those edges have direction ei minus ej, where ei is the standard height spaces vector. It corresponds to exchanging the elements I and j. So I'm not going to go into this, but if you drop the requirement that your log concave polynomials are scale free, then you have to deal with polymatroids instead of matroid. And this is its own beautiful story introduced by Edmonds, Lovász, Postnikov, Mrota, and many other people. You simply replace sets, collection of sets, by collection of multi-sets, and everything works as you would imagine. And if you observe the so-called the theory of generalized irreducible, which is the class of polytops where all the edge directions are in ei minus ej. And they all comes from deformation of the so-called standard irreducible, which you're seeing right here. And the rule of the deformation is that you're moving the facets in facet normal directions while not passing across a vertex. That will preserve the edge directions. So one observation here is that clearly, if you think about what Plücker relations actually are, is that the GRDN, the final possible hyperfield points, are exactly rank D matroids on N. Just consider what Plücker relation says, and consider what Krasner hyperfield is. Krasner hyperfield has all the possible null relations, and is simply saying the very basic universal principle that if you have sum of things equal to 0, and if you know one of the term is non-zero, there must be at least one other non-zero term. This principle is valid over any field and any tract, and in particular for the final tract, which is exactly saying this. And that is exactly the symmetric basis exchange axiom of Whitney. And the realizability problems translates to questions about the image of the final map on the level of Grassmannian. So the points on the target are called realizable matroid, and the fibers are what geometers call the realization space. They have the structure of a variety or scheme over F. So the definition in general is that for a tract F and a matroid J, the thin Schubert cell Grassmann over J is the fiber of the fiber map over J. And this decomposes the Grassmannian into locally closed pieces. And the realization space of J over F is the torus quotient of this thin Schubert cell. You may have heard about the so-called universality theorem, which says that when F is a field, such a realization space can be as complicated as possible. And this has many possible interpretations. You can say that it's complicated as algebraic varieties, or as complicated as possible as topological space. Or if F is something like Q, you may have heard about the claim that the Hilbert's tensor problem over Q is exactly the same thing as asking about the non-emptiness of the realization spaces. And here is a theorem, a slight modification of earlier work done by my collaborators, Plücker and Lorentzian, which is in a sense like it has a topological proof like any other universal property, but provides a very useful point of view. The fact is that for any matroid J, there is a unique tract determined by J, the so-called universal tract of J, such that the tract homomorphisms from the universal tract is the same thing as points on the thin sugar set. It's the same thing as functors in the category of tracts. And the construction is sort of topological. And similarly, there is a tract Fj called the strong foundation of J, which represents the realization spaces. And their unit groups are finitely generated. And these universal tract and strong foundations are not super abstract things. It's something you can compute. There's an implementation, you tell what your matroid is and press enter. It tells you what your foundation is, for example. And using this framework, you can reprove or reformulate many of the classical theorems in combinatorics in the language of quote and unquote like mainstream mathematics. So there are many statements that that sounds very weird or strange or miraculous, like the theorem of Tutt, which says that a matroid is realizable over every field if and only if it is realizable over F2 and F3. Why is this true? Well, we may be able to prove it, but maybe a better way of thinking about this is to go back to the statement that the product of F2 and F3 is the initial tract F1 plus minus. So if you have something that maps to F2 and F3, and then it will map to their product. But if the product is the initial one, it will map to everything. And Baker and Lorentzian has many statements that, yes? There is an underline. So Grassmann thin Schubert cell, and the underlined one is the after torus quotient. So it's the realization space. So very minor difference.
And it's F3, right?
Yes. Okay. Okay, so this is our main theorem, which describes the space of log concave polynomials supported on J. Okay, so let's go back to our setup. Let's say J is a collection of D element subsets of N. Somebody gives you a bunch of D subsets of N, and I'm going to view each one of them as a monomial. And then I'm going to consider all the non-negative linear combinations of them and collect only the polynomials that are log concave. That is my set Lj, the set of log concave polynomials on J with positive coefficients. That's what I mean by polynomials on J. And the claim is that this space Lj modulo global scaling is homeomorphic to the thin Schubert cell of J over T1. And the right-hand side is not an exotic space. It's a very concrete space. So for each one of the Plücker relation, you will have an inequality imposed by saying that the product of Plücker coordinates form a side length of an n-gon if your Plücker relation at n terms. So it's a real semi-algebraic set defined by many inequalities. And the claim is that that space is homeomorphic in a canonical, in a sense, way to the space of log concave polynomials. And if you mod out the torus section, which corresponds to scaling of the n variables, then this is homeomorphic to the realization space. And formulating in this way just was for the simplicity, and the same holds more generally for the space of Lorentzian polynomials and the polygrassmannian over T1. So polygrassmannian is like a Grassmannian, but there is a Plücker coordinate for every one of the multisets, not just sets. So let's collect some corollaries. So this might sound like a rather exotic statement, but it has very, very concrete consequences that you can tell your calculus students. So first corollary is something that I obtained previously with Peter from them, which says that Lj is non-empty if and only if J is a matrix. In other words, it satisfies the symmetric exchange axiom. Or in other words, if the Newton polytope of your F is a generalized permutohedron in the sense that every single one of H is in EI minus EJ direction. Why is this a corollary? Suppose Lj is non-empty, which means that I should be able to find the non-negative linear combination of the monomials that makes the function log concave. I claim that there's a homeomorphism to the Grassmannian over T1, so there's a corresponding point there. And then there's a final morphism from T1 to K, and then that point will go to some point in Grassmannian over K, and we know that this is same as the matroid of rank D on N. So that's one direction. What is the other direction? Remember that there is a canonical section from the final track K to T1 that sends 0 to 0 and 1 to 1. This is the section of regular n-gons. So if Grassmannian over T1 is non-empty from the strata corresponding to J, that is same as saying that the J is a matroid, because there is another way now too. Another corollary, this time it sounds like a theorem in algebraic geometry, goes like this. The support of a volume polynomial of net divisors is a polymatroid. You take any projective variety, you take any net divisors, and you produce this polynomial. Coefficients are the intersection numbers, and you just remember which collection of net divisors intersects to 0 or non-zero. And if you collect everything that intersects positively, then it will form a polymatroid in the sense that the convex rule will have only edge directions EI minus E and EJ. Simply because any volume polynomial is a Lorentzian polynomial. Okay, let me continue the statement of the theorem. So we have reduced the study of the space of log concave polynomial into the study of certain type of Grassmannian strata. So what is this space, Grassmannian over T1? It has a surprisingly simple description. So suppose Tj is the universal tract of J, and I can assume that J is a matroid, otherwise full discussion is empty. Then the coordinate-wise logarithm of the Grassmannian over J of the T infinity, this is the so-called the degenerate tract, the limit of Tp as P goes to infinity, is a vector space of dimension given by the rank of the abelian group, which is the unit group of the universal tract. So this time, over T infinity, the Grassmannian is a linear space in the log coordinate. Why? The degenerate tract has many, many null relations. So in particular, any 3-term relation, any 4-term relation, they are always null. So any Plücker relation is a 2-term Plücker relation. which means that it's a binomial relation, quadratic binomial relation. If you look at that in log coordinate, you will see that it's a linear relation between the logarithms of the Plücker coordinates. So it's a linear subspace, and the statement says what is the dimension of that linear subspace. And all our Grassmannians over Tp for any p will live inside this universal linear subspace. And the statement is that logarithm of the T1 Grassmannian is homeomorphic to the open subset of the closed unit ball of log Grassmannian J T obtained by removing the T0 points from its boundary. And this explains our mysterious Peterson graph example. If you remember. So for example, if your matroid consists of all true element subsets of 5, we are talking about the 5 by 5 Lorentzian matrices. And then we have seen that this is a manifold with boundary being S4 minus the Peterson graph. And now we know what is that Peterson graph. It is simply the thing that we remove, which is the T0 points, which is the beloved tropical Grassmannian. In other words, Grassmannian to 5 over T0. Okay, so again, this sounds like a rather abstract statement, but I'm going to tell you some corollaries with which you can tell your calculus students. And it produces many of the elementary statements that might seem surprising if you see for the first time. So here is the example that was most striking when I first saw this. Suppose you have a binary matroid. This is simply a matroid that's realizable by a vector configuration over F2. For example, any graph is a binary. And you can show that the matroid is binary if and only if its foundation is F1 plus minus or F2. Because not many things maps to F2. Examples include graphic matroids and some of the non-graphic binary ones, including the famous funnel plane of all 7 points on P2 over F2, as you see here. And the statement that follows from the general theorem I showed you before is that if J is binary, then Lj modulo scaling action is a point. In other words, there is only one log concave polynomial that you can produce by taking linear combination of the monomials corresponding to elements in J. For example, take 7 points in P2 over F2. 1, 2, 3, 4, 5, 6, 7. So there are 7 variables, x1 to x7. Consider all 3 element subsets of it. 7, choose 3. There are 35 of them. So we are talking about taking linear combination of 35 monomials. But I want it to be supported on the funnel plane, which means that I'm not going to use the 7 monomials corresponding to 7 lines, like 1 to 4 in the picture. So I'm left with 28 monomials. And I can take any linear combination I want, so long as it's non-negative linear combination of those 28 linear monomials. And then I ask, how can I make the linear combination log concave? And log concavity is like a semi-algebraic condition. You just want some determinants to be non-negative. And it seems very reasonable that I have 28-dimensional space of coefficients to choose from, and I have some finitely many inequalities. So it looks like I have like a 28-dimensional space. Maybe I scale out the 7 coordinate scaling, so maybe I have a 21-dimensional space. It's completely reasonable. The fact of the matter is, and this can be the challenging extra point exercise to your next multivariable calculus student, is to show that in fact, there is exactly one way of achieving this. Why? Because the whole space is isomorphic to the realization space of Lj over T1. And if you know that its foundation is like that, then simply the dimension of the manifold with boundary we are talking about is too small. The rank of the unit group of the foundation is 0. So tomorrow, I'm going to show you how to pose the very general realization problems in this setup, going back to questions in convex geometry and algebraic geometry. The goal is to understand how the volume polynomials in algebraic geometry sits inside these various Grassmannians over triangular hyperfields. Thanks for your attention.